All right, thank you, Kobe. Thank you for bearing with me at this late hour. So it's been a lot of fun to be here. So what I'm going to talk about is work that thoughts and work we've been doing in the last 5 years at Google, trying to think about how to read text and understand it. So I'll start with a little anecdote, a little story, and then go into some more details, and then end with a case study. So the anecdote is this very beautiful mountain called Mount Shasta in Northern California that I'm very fond of. And actually, if I search for Mount Shasta, this is a slide that I took a little while ago, so the display might be a bit different today. But besides a bunch of the dreaded 10 blue links and some ads, there's this thing here which was launched by Google a while ago called a knowledge panel. And it incorporates a bunch of information, some of each structural information. Say, it really knows there's some record somewhere of this mountain, Mount Shasta. You have a topo map of it. You have a bunch of attributes like elevation. And I'll tell you, the elevation is real because it's not. It's kind of exciting to get up there in out of breath. And a bunch of other information about it, like it's a volcano that erupted a while ago, and so on and so forth. And other related information, for instance, other mountains, most of which are mountains in California. In fact, all of them, I think. No, all volcanoes in the Pacific Northwest. So what you have here is text, and what you have here is some text and a lot of structured data. The theme that I'm going to discuss today is the connection between these two sides. How do we develop this connection, or how we can make it bigger and better? And so this thing here, it's based on some data structures called the knowledge graph that have been built at Google over the last few years, and it's all based on linked data. The knowledge graph contains entities of many types, and the entities of those types are linked to each other or into attributes. It's in a very large graph with many edge types representing different types of attributes and relationships. So including things like and so on. These tips. Now, suppose I really want to know something interesting, like, not just about the mountain, but how I climbed it. So now the story gets a little bit more complicated. So to climb a mountain, I need to find a trailhead to start from. And if I search for Mount Shasta trailhead, some links. And if I do a lot of research on these links, actually that one does not help at all, as it turns out. This one is the one I want. And so let's look at that. And I get this thing. And, there's a lot of text here, which is a quote from some book, which is actually a really nice book, but not very relevant to my goal of climbing the mountain. And if I go way down here and eventually get this information, which describes the main trailheads. Notice this is text. Now, this concept of a trailhead is a very useful concept to a climber or a hiker, but is not represented in the knowledge graph. There's all sorts of attributes like their elevation, like, for instance, 6,900 feet, which is not explicit, is not an explicit attribute. So what I really like to do, I don't like walk down mountains, I like to ski them. So I'm going to ask about Mount Shasta ski routes. Again, I get links. I don't get there. This is a concept. It's not in the knowledge graph. And it turns out that most of these links are useless. That, for instance, is about a ski area, a little ski area next to Mount Shasta, and so on and so forth. They are all useless. It turns out that's the one that I want. Now, I get there, and I get the same information I had in that knowledge panel. Okay, but it's not so useful for me now. And then way down, I finally find what I'm looking for. And what's interesting here is that I have all this interesting information, which is structured, but not structured ready for me to query with complex queries, but rather as a table, an HTML table of useful information, which is not directly accessible to me as a sort of a search subject to take it apart and look at the detailed information. For instance, even these various ratings here, which are very, very useful, are just little crosses, right? In the numbers, they are not things that I can ask about. I cannot say what's the easiest route, the ski route on Mount Shasta, right? So the lessons so far, one is this kind of slogan that various people at Google have been using for a while, called "things, not strings." IR is great, but if we actually have some real structured information about the objects we're searching for, we can give you more precise answers. So that structured information, one of the critical things it gives you is a semantic index, an index where the elements are not just words or terms, but rather information that has some intended interpretation in terms of where its structure carries a meaning for the user. And in addition, and this is something which is often underestimated, is that by having these objects in this knowledge graph, you have the nodes of the graph serve as unique keys for doing joins, for doing composition, for doing various kinds of complex algebra over the information you have, and therefore answer complex queries. But the problem is that most of the information we have so far is still in text. We have this large knowledge graph, it's growing all the time, but most of what's out there is still text or the sources. So what one of the areas I've been working on with my team for the last few years is how to link things and text. That is, how to link knowledge structures like a knowledge graph and text. And sort of I use this slogan, LowPass Semantics, because I don't want to give the impression that we are anywhere close to really understanding all the fine detail, the high-frequency part of meaning. What we're focusing on in very simple and important things about translating terms from text into and connecting them, linking them to structured data we know. So we have natural language text, we have these knowledge bases that provide key spaces, and we have also semi-structured data, which there's a lot of work on going on at Google as well, but I won't discuss. And we're going to accept that there's a lot of little detail that we cannot get, but if we can do these linkages, we can do certain useful inferences and we can get at some aspects of meaning that are important to for answering queries. So now, one of the things that we have been focusing on as well is that we don't just take the text as a sequence of words or sort of, but we're actually going to try to analyze it grammatically and semantically to support the kinds of inferences we need to do. Now, there's a bunch of levels that I will not talk about, except one example coming up, which is stuff in gray, like finding the grammatical structure of the web pages we have, finding what these various expressions say, what types of things we're talking about, whether people, organizations, locations, finding what pronouns, for instance, refer to, also which we do a lot of work on, deciding what particular entities names in the other referring expressions in text refer to in the knowledge graph. All of these things, which are extremely important and complex, I will not talk about here because what I'm going to focus on is the mapping from looking at entities co-occurring in certain contexts to the inference that there are certain relations between those entities. But let me show an example of putting this all together. So to feel it. So here's a little paragraph sentence that is came from somewhere on the web. And here's some how we do syntactic analysis of that sentence using part of speech tagging and dependency parsing. And Next, you see that we identified different phrases like Eric Wessner and parents and Poland and his, and I highlighted them as important phrases for the next stage of processing. The color coding also encodes a guess as to what kind of entity this is. It's a red person's yellow locations, for example, here. And furthermore, we can do some aggregation of this, that, for instance, there's this person, and we think it's masculine. We have some guesses to Eric might be a male, and it has a canonical name that we infer, and then a bunch of mentions. Eric Wessner, he, and his are all references to this particular individual. And there's some parents which are a type person, but we don't know much about them. There's a location, Poland, and we actually can link to the country Poland, and the town, a city, Raleigh, North Carolina, which we can also link to that. This is a real example run through our real system, and we can do this kind of processing over very large masses of web text in multiple languages. Next, so we also have certain rules that we've learned, and that's the topic of the rest of the talk, although these are from a different system, that say things like, if I'm looking for this person's place of birth, and actually I might look, for instance, that he is the subject of a passive construction of the form born and raised somewhere. So if X is born and raised in place, then that place is X's place of birth. Place of birth is a relation, an attribute in the knowledge graph. It's not it's not something that I directly connect to the text. The text doesn't talk about place of birth, says that he was born and raised. Notice also that here I don't have Eric Wessner, I have he. I had to be able to link to this pronoun to its antecedent to figure out that this is a claim that Eric Wessner was born in Raleigh, North Carolina. All of these inferences are inferences I want to do automatically, and we do automatically. Now, you might say, an IR person might say, well, all this, why are doing all this parsing, all this kind of complicated linguistic stuff? Because clearly, you could do that kind of thing directly from the words. You don't need, IR has served us very well. And I'll give you some numbers. So we did some experiments with extracting relations like that from text. And this is a little sample. So if I use patterns directly from text, I get some numbers of extractions of known triples, that is, things I know for sure are true, and then and we have some other criteria to guess whether something might be true. We have some more that we think are correct. Now, if I parse the text, I almost triple that, or more than triple that. If I do coreference, I almost double that. So basically so if you look at these numbers, basically doing these increasing levels of analysis, and the other thing which is interesting here is that I use this slow, accurate parser and this fast production parser, and using the fast parser doesn't lose me much. A little bit, but not much. So basically doing this depth of analysis of the text really is valuable if you actually try to get to the meaning of the text. So actually, I want to say, this is a little detour, but I want to have it here because there's a lot of confusion about the relationship between academic work and industrial work in this area and the other areas, all of these areas of big data. And because I like to distinguish between research, which explores what's possible, and product, which is about what's effective. And these are very, very different. Often you hear, 10 blue links, that's passé. We're going to do all these beautiful new things. But the questions you want to ask that person is, does your new solution have enough impact on actual search or actual product use to matter to users? Does it have a high quality that's high enough that the users will not be disappointed? Does it dominate incumbent technology, things that are easy to use and are well established? And finally, does the impact make up for the increased resources that are needed? All of these issues, which are obvious from an engineering and product point of view, are often ignored when people kind of criticize the state of the art in search or related areas. There's always this question saying, well, why do people do things the way they do now? For instance, why do our search engines the way they are now? It's not simply because the search engine companies are idiots. It's also because they had to consider this criteria. And often they have lots of research that is very cool, but does not necessarily meet all of the 4 criteria. It might at some point in the future, but it does not yet. So the point is, most research results that you know about, that I know about, most of the research that I do fails those tests. And sometimes it fails those tests for several years, and then it passes them because we have a new resource that helps us. For instance, in our case, there are many things that we were doing in this area before we had this knowledge graph resource that that we could not do anything with, and now, in fact, are usable in products. So I'm going to give this case study. This is research. This is not, I'm not making any claims about the product worthiness of this work, but it's an interesting vignette of research about using large-scale learning to learn how to map from co-occurrence of entities to relations. This is work I've done with Amar Subramanian and Neil Awa, colleagues of mine in Mountain View, and William Cohen is a faculty at CMU. Neil used to be a student of Williams, and we published that YAMNLP, which is one of the top natural language conferences last year. So what we were looking at is the following. Suppose I have a knowledge base, a free base, which is a free version of the knowledge graph we have, and we have some text on which you do the level of analysis that I described, and we have ways of linking between these two. So, for instance, I know that this person here, I hypothesize is the same as that string refers to that person in the knowledge graph, and she refers to the same one via coreference, and you have all these dependency trees that represent the various grammatical relations between the words. And what we're going to do is the following. We're going to think about chains of relations in this structure. So, and I'm going to allow myself to go forward, follow the arrows, and also backward, take the inverse relation. So I could imagine, for instance, go from Charlotte here to this Bronte to Wright to Jane Eyre and to there. So this would give an example of a way of saying that this person is an author of that book. So this is what the sort of the formalized knowledge, and this is the written rendering of that information. So this gives me a positive example of how I would say in text that this person is an author of that book. So we're going to take this sequence of labels, in this case, entity resolution -1, write, and then mention. So mention -1. Sorry, that's what I don't call it. Mention -1, write, mention as being quite a way of implement as a particular example of this particular of the sort of as the graph, the free base rendering of this particular sentence in English. So we're going to use these paths, sequence of labels, and as we call path types, because we're only looking not at the path itself, but the labels along the path. And they're going to consider random walks in this graph, where we go both forwards and backwards through the edges. And what we're going to do is to learn type weights, that is, weights over sequences of those relation labels that favor desired walks. Desired walks are, for instance, the walk that says that if I want to say right, then this sequence of things, kind of through here, is a good way of saying that. So there's this algorithm that William and Need developed over Need's dissertation, and which is called path ranking algorithm, which essentially you're giving a directed age label graph, you have some sources, some intended targets, and you ask yourself, if I observe this thing, is there also an edge label R that I didn't see? That is, should I, in fact, if maybe the graph is incomplete, could I hypothesize that, in fact, there is such an edge, it's just I didn't have it in my partial evidence for the graph. So we have these path types, which I write by pi. Here's an example of one. And we're going to, what we're going to do is to develop, essentially do a logistic regression model. It says, what's the probability there is a relation R between S and T? Well, it's basically going to be proportional to sort of a linear model that has where you have some parameters to be learned, theta, and the probability that the random walk would actually take me from S to T. So it's going to essentially, you weight by the probability of the random walk, and then you have these parameters tell you, if I were to get from S to T in my random walk, how much would I like that as evidence for the relation R obtaining between S and T? So you have these weights, you have these feature values, and if you do some feature selection, I won't go into, in some cases you do need feature selection, and you train this by regularized logistic regression. So let's do a case study. Here's a medium-sized problem, although it needs some parallelization. We have Freebase, which at the time had 21 million concepts, nodes, and 70 million edges. We're going to study three relations, profession, nationality, and parent. Stats here, there were 2 million people in Freebase back then. Of only 300,000 of those had a recorded profession. Very, very sparse. Very biased politicians. Of those, 250,000 were politicians or actors. None of you was here, unless you have second lives I don't know about. So we're going to generate automatically training data for the relation of interest, say profession. And we're going to we have to be careful in doing that. The edges for which we actually know the relation in the knowledge graph in Freebase already, we have to be careful because there is these frequent targets like actor that have a lot of fan-in. So we basically discount those divided by square root of the count so that of the fan-in, so that we don't take too many. Basically, don't want too many actors or too many politicians. You also want computer scientists and the gardeners. And then you hypothesize that pairs that are compatible with the relation according to their types, but not in knowledge base, you also subsample those in some way. And there are better ways of doing this, which we are working on now. And then we do the text processing I described, and I'm using here another example. So we do part-of-speech tagging and dependency parsing, and we do the various things we did. And we do coreference resolution using an algorithm which is a derivative of a well-known published algorithm by Agege and Klein, although improved in a variety of ways. And we do this concept resolution to the Freebase. We do a very simple thing. We just pick the most likely concept for named mentions in each coreference cluster. So for instance, jazz musician and Miles Davis here, we just picked the most common interpretation of Miles Davis, which was the jazz trumpet player. And then in Freebase, you have some information about that particular individual. So we go to do the linkages we described, and we have an example here. So we use around 60 million web pages that are all the web pages that are linked by this very simple method to Freebase. And that's dominated by frequent concepts. So Barack Obama, for instance, appears a lot. So we, again, do subsampling these sentences. And so to kind of complete an example here, you have the connection between the text graph, and a bunch of other pieces of information. And so this is a fairly large graph. So you see 2 billion nodes, 5 billion edges. And so this has to be parallelized. So basically we do some pruning, which I won't go into, which is distributed, what are we looking for, and exploring parallel map step, and then aggregate path types and reduce step. And the text graph, which is used, is indexed by dimensions, the entities we're looking for. So here's a learned part for profession. This is a concrete sentence that appears somewhere. And we conclude that, basically, if I go from, let me just complete that. So if I know that John Coltrane was a musician, Miles Davis and John Coltrane appeared together, so maybe Miles Davis is also a musician. So the path that goes mention, conjunction, mention minus, so mention, conjunction, mention minus 1, profession is a suggestive path for having the same profession. People that conjoin together often have the same profession, but not always. This path can be wrong. But so we take many of these, many path types like this, and we then combine them, and that's what gives the method the power. So to give the power of this method, so if I just match against known triples, we see that profession, we gain quite a bit by combining knowledge base and text over extract, or over trying just to extend the knowledge base by a similar method, or just the text. I ignore this column, we don't have time to go into it. Nationality is even better, it's actually very good. This is MRR, mean reciprocal rank. And parents is pretty bad. That's because the types are not too discriminating. Many people are related to the individuals of interest. They could be siblings, they could be cousins, and so on, husbands and wives. So it's actually, we cannot discriminate. Whereas nationality is different type from a person. They're only one. Basically, the random walks that lead from a person to nationality are far fewer than the number of random walks that go from a person to another person. So if you do a human eval, the precision of 100 is quite high for profession. It's actually high enough to go directly into the knowledge graph. It passes the quality standards, and in fact, things that we've done along these lines have gone. For nationality, also, we can get very good results. For parents, not good enough for prime time. And the other thing which is interesting is coverage. So if extract profession triples, so person, relation, profession to a particular profession, you're getting a lot of new triples. Like, so for instance, if I have 100,000 level, 79,000, almost 80,000 are unique. Now, we don't know whether they are all true, but we know that we probably can count to be around 90% precision, which is a fairly good output. So, this was an illustration that, in fact, we can use these massive methods to start getting a little bit to the meaning of text. So it's absolutely essential to have capable language processing components. And we can think now of the web as a huge and very noisy knowledge base. And we're going to try to combine it with the knowledge base we have already and amplify it. So we're combining multiple weak sources, these random walks, which are very, very shallow patterns. And we get it combining both from the text and the structured data together. And we can support some useful inferences. So, for instance, professions and nationalities for people we didn't have that information for. So that's all. I just wanted to, because I'm the last speaker, I'd like to give some thanks here. One for staying through to the last talk, which is I know it's late. To the organizers for this great program, which was really informative for me. And last but not least, to the wonderful staff who made this really work well. And it's been great. So thank you.